And thanks everyone for joining today. So a quick introduction, like Sam said, my name is Gabriel Curry and I am a staff member at CCEM. And today I'm going to be giving an introduction to the first steps when we're talking about starting a data analysis for Atom Probe after our reconstruction. And so I've made this talk at an introductory level. So if you don't have much experience with data analysis, but are interested in learning about it, then you're in the right place. If you do have some experience, hopefully you'll still learn something new today. So I'm going to start today's talk with a quick refresher of the basics of atom probe tomography. And then I'm going to jump into the good stuff, focusing on data visualization methods. And I've tried to divide my talk into two areas. The first, starting with the simplest way to visualize our data, which is our 3D atom map, and going over different ways we can divide our data into small subvolumes, such as clipping the data or creating regions of interest, ISO services, or volume renderings. In the next part, I will discuss the different ways we can quantify these subvolumes using bulk compositions, 1D profiles, 2D contour maps, and even 3D profiles. And then I'll finish up with a quick summary. Okay, so let's start with a quick recap on the basics of APT. Please note that there are two more detailed talks about data acquisition and reconstruction, and they can be found by checking out the past two webinars on CCEM's YouTube webpage. Okay, so atom probe tomography is a unique method as it uses the atoms of the sample itself rather than an imaging media like photons or electrons that interact with the sample. And how this works is that we start picking apart our sample atom by atom in a controlled way. And these atoms, as they leave the sample, we're able to measure things about them and identify them. And then we can use this information to build an atom by atom reconstruction of the original material. So how does this process work? Well, during an APT analysis, a high electric potential is applied to the tip under an ultra-high vacuum and cryogenic conditions. Field evaporation is then triggered by pulsing the high voltage to vary the electric field, or by pulsing a UV laser to vary the temperature. The mass to charge ratio of the evaporated ions are then determined by measuring their time of flight from field evaporation to their detection on a position sensitive detector, where their XY positions are measured. And then we can reconstruct our data into a point cloud of ions using each of its X, Y, Z spatial coordinates from the coordinates, as well as their elemental identity, which we define here as our mass to charge ratio. The XY information is gathered from the detectors using our XY hit information. And then the Z is inferred from our evaporation sequence of ions during the field evaporation process. And then for the elemental identity, we can gather that from our time of flight by plotting the ions on a mass to charge histogram or spectrum and comparing them to known masses of the elements and at given charge states. So once the reconstruction is completed, we are left with a 3D model shown here by the spinning data set, which stops spinning, that's okay, as well as our mass spectrum showing all the peaks of the different isotopes and the charge states, and these are all colored based on what type of ionic species they belong to. So for the remainder of today's talk, I'm going to be focusing on the different visualization methods that we can apply solely to our 3D model, and hopefully touch more on the mass spectrum in a future webinar. Okay, so visualization is a good first step for interpreting our atom probe data. There are several methods I'm going to introduce that are relatively simple to use and can be extremely instructive for assessing the distribution of ions within our reconstructed volume. So for this webinar, I'm going to be showing each visualization method using the commercial software IVIS. Please note that the CCEM is not in any way advertising IVIS or Kamika, which is the company that makes the software. It just happens to be the most common software, and it's the one used by our users at CCEM. So here we see a typical data workflow for an APT experiment. First, we have our RIP file, and this contains the raw data recorded during our atom probe experiment. Then we have our root file, which contains the reconstructed data, or the reconstruction data, which is then output after our reconstruction as a pause file, which contains the mass to charge ratio and 3D atomic positions of the reconstructed data. And then we compare this with a range file that contains a list of the ions and the mass to charge spectral ranges. So this is the IVIS display window, and it's typically divided into 4 regions for interacting with our data. So on the left side, with number 1, we have the main menu in the toolbar, and that's at the top of the screen. And this is where you can add to the projects tab, either by creating a new project or by opening an existing project. So there are 2 ways of starting a new project. The first is uploading your RIT file, which is our raw data, and then proceeding with our reconstruction, which is saved in our root file. And that's to create and that will create an analysis folder as the output. And that contains our pause file. And in this case, you can access the range file to go with your pause file by right-clicking the root file, which says recon. The second option is to upload a pause file directly and pair it with any range file. And this tree that I'm showing here is located in the Projects tab on the left. And beside this Projects tab is an analysis panel where you can access your 3D grid, your mass spectrum, and your ion ranges. And this will appear when you open your pause file. We also have a 3D display, which will also appear, showing our reconstructed pause file, in which a number of image manipulation tools can be found either on the toolbar at the top, as well as by right-clicking our different things in our tree in our analysis window. And some of these I'm going to be showing you today. And then finally, at the bottom, we have a panel containing our mass spectrum. Okay, so when we start our data analysis, the simplest way to visualize the data is to represent each ranged ion, or a fraction of each ranged ion, as a colored point or sphere in 3D space. And this is called a 3D atom map. So here you can see an atom map showing a ferritic steel sample containing some retained austenite, which we have highlighted, and I'll be showing you how you can do that today. So using our 3D point cloud, we can map different species individually. So for example, here you can see high density regions of carbon and manganese highlighting our secondary phase. We have a high density of niobium ions highlighting our particles. And we have a high density of our MO ions at our interface, as well as particles. So for those using IVIS, you can right-click on the reconstruction, and this will pull up a drop-down menu. And from here, we can click Display Ranges, and this will pull up a new window. So using this window, it shows the different ions, and we can select them to show them, and we can also edit their color. You can also set the percent or the number of ranged ions that you want to be displayed in your 3D image. And then once you have that shown, you can select how you want them to be displayed. So it's either by points or by spheres. And then we can adjust their sizes as well as show the max number of spheres you want to be displayed. So there's lots of options to show our data in this point cloud. It's also important to note that this list shows all the ranged peaks, both atomic and molecular. So if you want to show all ranged carbon, you would have to select not only our carbon, but also our molecules of carbon. So C2, C3, C4, etc. So once you have a desired atom map, so here I'm showing carbon, there are a few ways to isolate regions within the data for a closer look. So the first is by clipping our data, which enables you to remove ions in the X, Y, and Z planes of our 3D data set. So this can be done by selecting our clipping control tool. And this can be found in either the toolbar at the top of our 3D display or under the display controls found, again, by right-clicking our 3D window. And here we can see our clipping tool. So once we select that, it'll bring up this window where you can click and drag the sliders on either end in our X, Y, or Z axis to remove ions from your display. So for example, I've dragged the slider inwards in our X axis, and that's isolated a plane in my data set along that axis. And here the numbers are representing our thickness in nanometers. So then once I have this slice, I can then rotate my reconstruction and look at this cross-section head-on. And what's nice is that I can export this clipping by right-clicking the top-level ROI in the left analysis window, and then clicking Export Clip File or Pause File, and then I can analyze this volume further, or this sub-volume further. Another way to isolate a region of interest within the data is by using a shape of your choosing, such as a cube or a rectangle, cylinder, or sphere. And these ROIs can be easily created by right-clicking on the top-level tab in the Analysis panel and selecting Create New ROI. Once you do that, a dialog box will pop up, and this gives you parameters for what shape you desire. So here I've created a cube, and then I can adjust the size, location, and rotation of this cube. And here I've put it on my carbide particle. And I can do this either by using this, this wheel here, which will be found in the center of the region of interest. And this allows me to adjust the size if I want to make it bigger or smaller, the location where I want to put it, as well as rotate the cube. I can also do this on the left side in the Properties tab. It also gives you the option to adjust your dimensions as well as the position. And just like with the clipping, we can right-click on the ROI and export it. And this can be done either by choosing our ions inside our region of interest or outside our region of interest, depending on what you're looking for. And here's an example of our isolated region of interest, which now we can analyze further. So hopefully you can see how the clipping tool and the ROI tool are great for sampling a plane or a simple shape. But what if we want to isolate a 3D volume that's more complex based on a characteristic of our material, such as density or concentration? Well, for this, we need to define a grid of data locations first, where each location on this grid corresponds to a small volume, which we call a voxel. So most commonly, by doing this, we can then characterize the atomic contents of that voxel. And this is most commonly done by measuring either the density or the concentration of a given element. And that's usually with respect to the contents of the voxel itself. So in IVIS, a 3D grid is automatically created when a pause file is opened. However, it can be edited by right-clicking our 3D grid, shown here, and selecting the 3D Grid Properties tab. And this will open a new dialog box where we can then select the X, Y, and Z dimensions of our voxel. So the selection of the grid size, however, you can see that the initial grid that's created in IVIS is a cube. The size of this can be adjusted. However, it requires some balance between positional error and statistical error. So for example, if the voxels are too large, fine details may be lost from the analysis. However, if they're too small, the grid leads to higher statistical error, as some of the voxels may not contain any ions or the ions we're looking for. So in most cases, the blocks will ideally be close to cubic in shape and position, so you won't have to change the shape. The only thing is if you want to change the size of it. And this, using a cube, helps to ensure that a spatial correlation exists in the data and it's reflected correctly. So there exists a probability that an atom occurring within a given voxel was imprecisely positioned and should have been associated with a neighboring voxel, or that our 3D grid may be divided or dividing small fine features because there's no relationship between our grid and internal features in our volume. So to limit these effects, the commercial software applies a delocalization algorithm to smooth our data, which you can see an example here. And this is also schematically shown here. So instead of each atom or ion making a single contribution to the counting stats at one point in our 3D grid, a weighted contribution is instead made for each of the neighboring grid nodes based on the ion's proximity to each of these points, which we can see here. So in IVIS, the amount of this smoothing in the X, Y, and Z dimensions can be adjusted again in our 3D grid properties tab, if desired. Okay, so using this 3D grid, another way that we can quantify our data is by defining a surface at a given threshold. And this is referred to as an isosurface. So this analysis works by isolating blocks in our 3D grid, having a specified range of composition or density for a given element, and then combining an array of adjacent blocks with the same defined range to create our isosurface. And this isosurface then appears in our reconstruction as a highlighted region, which you can see here. So if we look at our example and we want to create an isosurface, we can right-click on the 3D grid, and then we can select our Create New Isosurface. A dialog box with parameters will pop up where we can select the type of profile we want to use, whether we want to use ionic or atomic calculation, and then the ion of interest. And then by selecting OK, it'll prompt us to the isosurface properties box where we can select the threshold that we want to use. So here I've selected to create an isosurface for manganese using a threshold value of 5 atomic percent. And we can use this again to isolate our carbide particles, again using an atomic percent of 5%, atomic percent of 5%. So this is our threshold for both manganese and carbon, and we can start showing different features using these isosurfaces. So after you've created, after you've selected your Create Interface button, a list of all our isosurfaces will appear in the analysis panel. And you can click on any of these isosurfaces to view more information on them in the properties window that will appear below them. And some information you can get are things such as our surface area, our volume, or you're able to disable them if you don't want to show them in your reconstruction. So you can easily sort through this list by right-clicking the interface group at the top, where you have the option to start sorting using several parameters, such again as surface area, volume, ID, etc. And this same list can be brought up by launching the analysis panel, which is a window like this. And again, you can see the same information is viewed in table form. And then finally, we have a volume renderer. And this is a tool for looking at the concentration or the density of the 3D grid using a given ion type. This can be done by selecting the volume button in the isosurface properties. And this will prompt a dialog box like this, where you can adjust a few different viewing parameters. So for example, if you can change your parameters using this toggle. And you can change either our mapping of voxel values based on their degree of opacity, which you can see here, or by mapping the voxel values using a temperature color map, where blue represents our minimum value and red represents our maximum. With this second option, you can also enter a value to define the opacity in this volume rendering. So in addition to segmenting our data into small regions of interest, or by using our 3D grid, which I've just briefly gone over, we can then begin to quantify the atomic contents of these regions. And the most common way is by using concentration. So the simplest way is by measuring the bulk composition. And this can be done by right-clicking from either the top level ROI to do a full volume bulk composition of our sample, or by selecting an isolated region of interest or isosurface. But in both cases, you right-click and then you can choose to display the bulk composition. This will then bring up a table where you have the option to display your data in 3 different ways. So first there's ionic, and this is representing the concentration of an ion determined by dividing the counts of that ion by the total number of all ranged ions. You can also do it by our atomic option, and this represents a weighted ion count, taking into account all the atoms in the ion. And then finally, we can, having the atomic selection selected, you can then decompose it to represent all the ions broken down into their individual atoms, which you can see I have here. So next, we have a 1D concentration profile, which is a plot of the local composition along the length of an ROI. And this is usually done using a cylinder or a rectangle. And this can provide us with useful information on composition fluctuations, especially in the regions of our interfaces. So the first steps in creating a 1D profile is to select the volume you want to analyze within your 3D data. And we can do that using a region of interest. So here I position my ROI across my interface. Once this volume has been selected and correctly positioned, we can right-click on the ROI, shown here, and we can select Create 1D Concentration Profile. A dialog box with parameters will then appear where you can select the analysis access that you want to use. So if we imagine our ROI, we can divide this, divide the data into small slices, which are perpendicular to our analysis direction. And then we can measure the concentration of all the elements present in each of these slices. The size of the slices may be defined in terms of either a fixed sample count of atoms or a fixed bin width. And these parameters can be selected by right-clicking our 1D profile, and then at the top here, there's those 2 options we can select. So it's good to note that when you initially create your 1D profile, you're going to get a preview profile. So this is generated, and you can use this initial preview to help you better orient your region of interest around your feature, as well as resize it in order to capture the feature better. And then once you're happy, you can then go and define your profile further using our either fixed sample count or a fixed bin width. So here's a 1D profile, and we clearly see fluctuations in concentration across our interface between our ferrite and our retained austenite. And as you can see, the 1D profile is a rather simple way of displaying our data. However, there are a few things that you should keep in mind. So larger slices will produce less statistical scatter in the measurement, but they will reduce our spatial resolution. Also, local magnification effects can affect the position of our ions in the reconstruction, which will be reflected in the 1D profile. And this includes inaccuracies in the width across our interface and the width of our interface and the compositions across it. And again, that will be reflected in your profile, so that's something to keep in mind. Okay, so as you can imagine, the 1D profile is most useful when working with flat interfaces. But what about a 3D volume, like our particle? So once you have defined an isosurface, an alternate method for a concentration profile is something called the proximity histogram or a proxygram. So a proxygram is similar to a 1D concentration profile, but instead of calculating a profile along an analysis axis in our ROI, the proxygram calculates the profile with respect to distance from an interface. So using a defined isosurface, the local atomic neighborhood adjacent to the interface is examined. And atomic positions are correlated with respect to their distance to the normal of the isosurface and used to generate a histogram measuring the population of atoms in a series of shells, which you can see here, at increasing distances from the position of the isosurface. With this, a concentration distribution profile for any species can be generated. So a proxygram can be created by right-clicking on an interface in the analysis panel and selecting Create Proxygram. A dialog box with parameters will then pop up. And there are a few important parameters to consider here. So the bin size, which represents each slice of the profile, the maximum distance, which sets the distance from the interface for which the proxygram is going to be calculated. So that represents this axis here. So we have our distance into the feature and outside the feature. And then finally, we can, this option here, compute proxygram for one ion out of every parameter. So this is the percentage of the data that will be used to create our proxygram. So for example, entering 1 will use 100% of the data, whereas entering 2 will use 50%. It is important to keep in mind that the proxygram will be influenced by the choice of the isosurface used to characterize the interface, and thus it's dependent on our 3D grid. So it's best when it works best when we're working with more simpler 3D shapes, as well as distances closer to our interface. So a final way that we can quantify variations in local composition is by a 2D concentration map. So these maps show the distribution of selected ions in a plane perpendicular to the analysis direction of an ROI in which it's created from. So the contour map is calculated by dividing the region of interest into a 2D grid of blocks in the lateral XY plane. So each point on the map represents one of these blocks, and its color indicates the value of the concentration or density measured at that XY coordinate. The thickness of the region of interest needs to be adjusted to better optimize the contrast of each map that we create. And this will help us emphasize particular features. So for example, if thickness is too small, it may fail to either incorporate smaller features, and it might limit the number of atoms available in the analysis. And that can affect the quality of our stats. However, if the region of interest is too thick, then features occurring at depth in the Z direction in the volume may overlap in our XY plane, and thus that will be reflected in our 2D map. So a contour plot is created by right-clicking our ROI, again in the analysis panel, and selecting 2D contour plot from the list. And then a dialog box will pop up, and then there are a few main parameters here that we should consider. So these main parameters are the distance between samples the distance between samples in our plane. So what this is saying is that it's the distance between our points within our XY sampling plane. And then we also can consider the distance between these planes, which is our Z direction. And then finally choosing the analysis direction that we wish to use. So over this talk so far, I've introduced a number of data visualization methods. So I want to kind of finish up with a quick summary. So overall, the reconstructed data can be analyzed using a variety of simple features to get us started with our analysis. So the simplest is our 3D atom map. And this map can be used to quickly just identify and isolate specific regions, either using our cube or cylinder or spheric volumes, as well as clipping our data. We can also divide our data into a grid of discrete volumes or voxels with atomic contents of each voxel characterized. And again, the most common is using our concentration or density. So this is why you'll see this option pop up in a lot of these dialog boxes. And we can use this grid to then define our isosurface at a given threshold. So now we can start looking at defining 3D volumes in our reconstruction. Next, we can take these subvolumes that we isolated and we can quantify the atomic contents of them using either point measurements, such as our bulk concentration, our 1D profile, our 2D contour maps. And then we can also use our proxygram, and we can kind of think of this as our 3D equivalent of our 1D profile. And this provides a number of advantages, again, while working with more 3D shapes that are not the same as our cube or cylinder or sphere, such as a cluster. Okay, so before I take any questions, I'd like to highlight some good reference material. I've used this for the talk today. And as you can imagine, they go into a lot more detail than what I've introduced today. So feel free to check these out if you want to learn more. So with that, I'd like to thank everyone for tuning in today. And hopefully you've all learned something new from today's talk that you can apply to your own research.
Abe, so please, if you have any questions, place them in the chat and Q&A. Currently, I don't see any, so we'll just give we'll give folks a minute or two to type them out. Oh, there's one. Chen Gu is asking, how can we get the volume of the tip?
So the volume of the tip. So that should be displayed. Let's see if I can. Oh, my mouse is going crazy. There we go. So when you upload your data, all the way back to the beginning. When you can select your top level ROI, and you'll be given a whole properties box. And there's a whole bunch of features that we can, information about your full volume itself.
Great. Farzan adds, thank you so much. Amazing. Is there any limit on the chemistry of the material that we can analyze with this method?
Sorry, can you repeat that?
Sorry. Is there any limit on the chemistry of the material that we can analyze with this method?
Yes, so the limitations, it depends on, for the chemistry, you can see from today's talk that there's a lot of user interaction. So the volumes that I'm defining, so that will, the grid size that I'm creating. So these are factors that can affect the quantity of our concentrations that we calculate. Also, what I didn't talk about today, which I'll hopefully do a future webinar on, is our mass spectra. So depending on how we do our analysis and the quality of our data, so our background levels, and how we range our mass spectra is also going to reflect the concentrations that we're measuring when creating subvolumes in our data set.